Thank you very much for clicking on this video. I am very happy to have you here with me. We are going to be looking into chemical combination. The first question is to answer what do we mean by chemical combination? Chemical combination here I say is the joining together of two or more atoms chemically. So here we are going to be joining either of the same atoms or different kinds of atoms. We make sure that it's more than one. The attraction that actually holds this process of chemical combination is what we mean by chemical bond. That is the attraction of force holding two or more atoms together chemically. We refer that to be as a chemical bond. And there is a reason why atoms have attractions. And there is a reason why they want to bond with one another. We know that not all atoms can exist alone. So one of the reasons why atoms want to bond together is because most of them don't exist alone. Most of them, like the atomic atoms, like hydrogen, fluorine, oxygen, nitrogen, chlorine, bromine, and iodine, they don't actually exist as a single atom. So they actually needed to bond together to give us their molecule. This is one of the reasons why atoms tends to bond together. Another great reason why atoms tends to bond together include the tendency of atoms from group 1 to 7 to look like group 0, which are actually stable and they are unreactive since they have their duplet state or octet state complete. That is, the electronic configuration of this group 0 has all number of electron complete or equal to the maximum number of electron required per shell. So each other atoms want to look like them. That is the second reason why atoms want to bond. So because of this second reason, we are going to look into electronic configuration of some elements. We're going to use it in order to explain chemical combination, because this is actually the major reason why chemical bonding occurs. If you look closely, you will see a simple diagram representing the first 20 elements, where we have hydrogen, helium, lithium, down to calcium, and the numbers of here represent what we call the atomic number. So the atomic number of magnesium is 12. The atomic number is the number of proton. Now the number you are seeing below, if you add it together, it will give you the number up. This number, I am referring it to be the electronic configuration of those elements. And the electronic configuration of those elements comes from the number of electron present in that atom as a neutral atom. So in a neutral atom, you're going to have the total number of proton being equal to the number of electron. And the proton we find in the nucleus alongside with the neutron, and the electron we see electron at the atom shell, or we can say we find them in the orbitals. If you look closely, you will notice that hydrogen ends with 1, lithium ends with 1, sodium ends with 1, and potassium ends with 1. This last number here make us to group them in the same column. If you also look at beryllium and magnesium, the same thing happens. Look at boron and aluminum, the same thing happens. 3 3. For carbon, we have 4 4. 5 5 6 6. So we actually group them based on the number they have. But if you look over here, we have helium. Helium is 2. That's supposed to look like this group, but it's not placed in this group, despite having the sign name of helium like beryllium. But we are not able to place it here. This is because this first line is K shell. The maximum number of electrons that this K shell can contain is 2. And whenever we have the number of electron equal to the maximum number of electron a shell can contain, we say that that particular atom has a complete duplex state or octet state, because the number is equal. So we are having hydrogen here to be 1, and we have helium here to be 2, and the maximum number of electron in this shell is 2. So we take it as a complete shell. So all these ones here are complete. They are actually unreactive. So each of these wants to look like this. Let's pick out lithium, beryllium, and boron. We are going to look at this like this. Lithium has 1, beryllium has 2, boron has 3. Now, according to observation, these values here, we call them valence electron, and actually call them valence electron number. So this number you are seeing here, 1, 2, 3, 4, is the valence electron number of each of the atoms here. Okay, this valence electron number in chemistry we have a different definition for it. It actually means the total number of electron that is found at the atomos shell of that particular atom. So if, for instance, I am drawing the shell of lithium, it will look like this. So this is the atomos shell, and the number of electron in lithium atomos shell is 1. So if we do the same thing for beryllium, we will have something like this. So the atomos electron is 2. The total number of electron at the atomos shell here is 2. So this one represents the valence electron of lithium. This represents the valence electron of beryllium. So this is a simple diagram representing boron atom, and we have 1, 2, 3 to be the number of electrons that are found at the atomos shell. This is the atomos shell. This is the K, and this is the L. K, this is the L. K, and this is the L. During bonding, this group, lithium, beryllium, and boron, that their valence electron number is between 1 and 3, they lose all their valence electron. That means that they are capable of releasing all their valence electron. And when they do that, they become an ion. Then, if any element is capable of releasing all its valence electron, then we can call that particular element a metal. So lithium, beryllium, boron can be rendered as metal, although boron in chemistry we don't render boron as metal, but as far as you are able to give out your all valence electron, we will render you as metal. So anyone that has valence electron to be 1, 2, and 3 is going to give out all its valence electron. Then the one that have something like 5, 6, and 7 is going to collect a total number of electrons that is going to help the atom to complete its octet state. For instance, let's use something like nitrogen. For nitrogen, if you look at this, the total number of electrons required to complete the shell of nitrogen, that is the L shell of nitrogen, is actually 3, but it has 5. It looks foolish for nitrogen to lose all the 5 electrons in order to look like the noble gases, but it will be much wiser for nitrogen to look for 3 electrons. From anywhere you can get the 3 electrons. So for nitrogen, what we are going to notice is that it's going to require 3 more electrons. If you look at this nitrogen very well, this is 1 electron standing without being paired like this one. These ones are paired. We call them paired electron, and we have here to be unpaired electron. Grab that. So we are going to be looking into attractions between metals and metals, non-metals and non-metals, and also we're going to look into between metals and non-metals. So we have seen nitrogen. You on your own, you can actually draw the structure of oxygen, that of fluorine, and you can go on to do that of sulfur, chlorine. Then I want you to see something here. In the observation, I said that lithium, beryllium, and boron can lose all their valence electron, but these can accept the number of electrons in order for them to complete their octet state. But I did not say anything about this carbon and silicon. Carbon has 4, and it requires 4 to complete its octet state. It is foolish for it to give out all its 4 electrons to look like helium, and it is not that easy for carbon to get 4 electrons to look like neon. So it is difficult for someone to give, or one of the atoms to give carbon 4 electrons, and it's also difficult for carbon to lose 4 electrons. Because of this, carbon, that is all the ones we are going to see in group 4, all elements found in group 4 cannot be able to accept electron, cannot be able to give out electron. Rather, what they can only do is to share their electrons. This is going to lead us to types of chemical bonding. We grouped elements into metal, metalloid and non-metal, but majorly we group them into metals and non-metals. So the bond we are going to look into a bond that exists between metal to metal bonding. We can have non-metal to non-metal bonding. We're also going to look into metal to non-metal bonding, and we're going to start with metal to metal bonding. Metallic bonding can actually exist between the same element and can possibly exist between different elements. We are only going to look into same elements. For something like sodium, potassium, calcium, magnesium, we're going to just use example from sodium to represent this. If you look at the diagram, you will notice that this represents the atomos shell of a sodium atom. So I am having here to be electron. You see how there is a cloud here, a cloud of electron. Now the forces between this cloud of electron and each of the nuclear charge, that is the proton charge of the metal or element, is what we mean by metallic bonding. So we can actually see that metal to metal in same element can give us what we mean by metallic bonding. Then what do we actually mean by this metallic bonding? From same element, what we have as a result of that is metallic bonding, and this exists between atoms of the same element. It is an attraction between the electron clouds and the positive nuclear charge of the atom. Mind you, this word electron cloud can also be called the delocalized electrons, or some people can even call it the free mobile electrons, which is any of them you see is correct. And the result of this metallic bonding will make that element to have a high melting and boiling point. Mostly they are solids, they have sonorous in nature. What I mean by sonorous is that they can actually give us good sounds when it is being heated. They are malleable. That means that when we heat them, we can actually shaping them the way we want, and they are ductile because it means what I mean by being ductile is that we can actually reshape them, draw them into lines. Yes, that's what I mean by that. Most of them have magnetic property, and they mostly have high density and are mostly solid, except mercury. The rest of metals are actually solid. So you have to grab that. That is the result of metallic bonding. Now the other one is different elements. That is metal from different elements. This will not give us a chemical combination. It's going to be a physical combination where we call that alloy, and this alloy is sometimes done in order to make that particular element to be used for a particular purpose. We have something like bronze. Bronze is a combination of copper and zinc. I can normally call it cozine. And brass is a combination of copper and tin, and I normally call it cosine. This is metal to metal bonding. So in metal to metal bonding, we have one chemical bonding there called metallic bonding. So I needed to keep this with you, that we have gotten one chemical bonding, because we're discussing chemical bonding here, that we have one chemical bonding from metal to metal bonding. Now let's go for non-metal to non-metal bonding. Thank you very much for clicking on this video. Don't forget to click on the share button and notification bell, and don't forget to share my link to your loved ones on your social media platform.